For the first question, we're asked to name the following compounds specifying E or Z alkene geometry as well as R and S stereocenters. For the first compounds, we have carbon number 1, 2, 3, 4, 5, 6, 7. So we have a heptene. I'm starting on this carbon rather than this carbon because this carbon leads to the second carbon, which actually has our bromine substituent attached to it, where this one does not. So we have an ethyl group at the 3 position, and this is a more prominent substituent right on the second carbon, so we need to incorporate this within the parent chain. So again, we've got 2 bromo, and we have an alkene at the 3 position, so we have 3 heptene, and we also have an ethyl at the 3 position. Now for the alkene geometry, our most prominent group on this carbon here is our ethyl with the bromine on it. So that outranks our ethyl group without the bromine, and on this carbon we've got a hydrogen competing with a propyl group, and the propyl group definitely wins. These are on opposite sides of our alkene, so we have an E alkene. Remember, Z is the same side, E is opposite sides of our alkene. And while we're at it, let's go ahead and specify the stereocenter as well. So for our stereocenter, we have hydrogen already in the back on A dash. Bromine's ranked number 1. Our carbon with the alkene is ranked number 2, and our methyl is 3. So this is an S stereocenter. So we have 2S, 3E, 2 bromo, 3 ethyl, hept, 3 ene. And remember that 3 indicating the starting point of the alkene could be here, or it could be there in front of the heptene. Either one is acceptable for IUPAC naming. For the next compound, I'm going to start here on carbon number 1 because it looks like I have a methyl group branching off carbon number 2. I have an alkene at the 3 position and an ethyl again at the 3 position, and 4, 5, 6. So the parent name for this compound is hexene. Looking at the alkene, on this carbon, my winner is the isopropyl group, and on this carbon, my winner is the ethyl group. So again, we have a E alkene. So for this compound, we have 2 methyl, 3 ethyl. So I'm going to start with 3 ethyl alphabetically. That comes before methyl. So it is E, 3 ethyl, 2 methyl, and I'm going to put the 3 in front this time just to emphasize it could go either way. So 3 hexene. All right, for this one, label the stereocenter on both and then determine whether they are identical, constitutional isomers and enantiomers, or diastereomers. In this case, I already know it cannot be a diastereomer. We only have 1 stereocenter. So this stereocenter is either the same. So this stereocenter is either the same or the opposite of that stereocenter, which means in everything else, the connectivity is the same. So they're either identical or enantiomers. So we need to decide what the stereocenters are and label them appropriately. So here, bromine wins. The carbon with 3 oxygens attached is second, and the methyl is third. 4 is conveniently in the back. This is an S stereocenter. And for this one, bromine is 1, that is 2, and our methyl is 3. 4 is in the back. We do the rotation. That is also an S stereocenter, which means that these are identical compounds. And again, based on what we talked about, so everything in the molecule is the same. So same compound, same connectivity, and same stereocenter. In this case, we have 2 S stereocenters. So if we're going to name these compounds, we would name them the exact same. Absolutely nothing would be different about them. All right, for this, based on the arrow pushing mechanism, draw the product of the reaction. So here I have my electrons on my hydroxide anion taking this proton, and then my electrons from this carbon-hydrogen bond move down to form the double bond. And then my bromine leaves. So my carbon-bromine bond breaks and my bromine leaves. So one of the products that I have is Br-. Another product that I have is a protonated hydroxide anion. So we've protonated that. Specifically, that's the proton we took. So now instead of OH-, we have H2O. And then my last is we formed an alkene. So these electrons here went down to form the alkene. That was a terminal alkene. The carbon is still bonded to an alkene. We still have our ethyl group on that carbon, and we still have our propyl group on the carbon here. And for B, we have a nucleophilic attack and a loss of leaving group. Our oxygen anion is going to do a nucleophilic attack on the CH2 of our 1-bromoethane. So we're going to form a bond between this oxygen and that carbon, and that leaving group is going to leave. So looking at our products, we have our ring structure, all that remained the same, our oxygen. Now the electrons went to form a bond with this carbon here. So I've drawn that carbon right here, and that carbon no longer has a bromine attached, but it does have a methyl group attached. So I'm going to draw that methyl group, and then our other product is Br, now with a negative charge on it. All right, for this, we made a diene product for 3A. So we have an alkene here and an alkene here. 2 alkenes is a diene. And this says that the diene product is more stable than the starting material, which means that the reaction was exergonic. So even if this was just given to you on an exam, this is basically telling you that it is an exergonic reaction. So draw an energy diagram where free energy is the y-axis, and the reaction coordinate is the x-axis. Show energy levels of the starting material, so I'll start right here. The transition state is going to be much higher in energy. It's an exergonic reaction, which means that our product is more stable than our starting material. So this is our product, this is the transition state, and this is the starting material. For the last one, we have an energy diagram. We've got our reaction coordinates, and we need to match these with the corresponding product. Really, these would be an intermediate of a reaction, but we're only showing basically part of the reaction. So in this case, this is our product of what we're showing. So this says, explain why the carbanion is higher energy than the deprotonated amine. So in this case, thinking back to Ario, the carbon atom is smaller than the nitrogen. It's also less electronegative. It has more difficulty holding on that negative charge, mostly because it's less electronegative. Carbon is significantly less electronegative also than oxygen, and then clearly less than nitrogen, and this has resonance with this other oxygen. So this is the least stable anion that formed. If it's the least stable, that means it's the highest in energy, so 4 is A. The second highest in energy is B, and that is the nitrogen with the negative charge on it. Oxygen is more electronegative than nitrogen. It can handle the negative charge better. That is the second most stable, is C. And in this case, now we have resonance. So we have a negative charge on the nitrogen, but this is the only that can participate in resonance. So we actually have two contributors associated with this. So one is there and one is there. So the other resonance contributor, if I draw the 5-membered ring here, is nitrogen. And now this nitrogen's double bonded to this carbon. And now that carbon is single bonded to this oxygen. And now oxygen has the negative charge. So we've got a double bond here, and now this is a single bond. Oxygen has our negative charge. So D is our most stable intermediate for this. It is the lowest in energy.